Hello everyone, welcome to IIT-JAM in Chemistry tutorial number 31, and this is lecture number 9 of the physical chemistry chapter liquid state. For the last 3 lectures, viscosity of liquid had been our subtopic, and in the third lecture of this same subtopic we are going to derive the master equation of all equations, the Poiseuille equation. First of all, we have to have an idea about the experimental setup before deriving this equation. Here, this is such a container where a fluid is continuously being added, and due to this overflow, the fixed level is continuously being maintained. Here, a capillary is fixed, which is cylindrical in nature, through which the liquid is allowed to pass through. And this height, constant height h, is continuously being maintained. Therefore, the capillary has length L and radius r. This liquid has density rho and viscosity coefficient eta, and the pressure at this point is the initial pressure which is being exerted due to this height h. So the height of water level for exerting the initial pressure is h. Now the pressure at this point, if it is P1 and if it is P2, then the pressure difference at this for this 2 points, it is P1 minus P2, which is written as P. Actually, the pressure at this point is 1 atmosphere plus h rho g, where g is the gravitational acceleration. And at this point, the pressure is 1. So this h rho g, this excess pressure, is being released at this point. But the 1 atmospheric pressure is present throughout the system. Therefore, the actual pressure at this point is 1 atmosphere, and at this point is 1 plus h rho g, so that the difference is 1 plus h rho g minus 1 equals to h rho g, which is in turn written as capital letter P. Now, after some time t, when the liquid is passing through this capillary, this liquid is collected in yet another container. It may be a beaker this time. And the volume of the liquid which is collected after some time t is V. Therefore, volume collected liquid in time t is V. Volume of collected liquid in t time is V. And from these parameters, we have to arrive at the Poiseuille equation, which is eta equals to P pi r to the power 4 over 8 LV. And if you put the value of P as h rho g, then it becomes h rho g pi r to the power 4 t by 8 LV. Now, this capillary is cylindrical in nature. So, this cylinder is drawn here like this, which has length L and radius r. Now, this liquid has viscosity coefficient eta, it has already been mentioned, and another point is mentioned, that the pressure difference is P. Now, if another imaginary cylinder with radius y is considered here, then how does it look? It looks like this. The shaded area is the tiny cylinder which has radius y. Now this cylinder is allowed to move from left to right with velocity u. And this cylinder at this point has area of contact, which is actually the circumference of this circle times the length of the cylinder. So it is the area of the cylindrical surface, which denoted as A. It is twice pi y into L, so twice pi L y. Now the cylinder moves at its wall with velocity u. Because at its walls, why this point at its wall? Because the velocity at different points are different. The velocity here is 0, whereas the velocity here is maximum. So the velocity, say, at this point is u. So the cylinder moves at its wall. That is why this wall, this word is added here with velocity u. So after some time t, how much distance does it cover? Now velocity into time. So look, the cylinder moves like this. Once again I am showing you, the cylinder is moving with velocity u at and moves up to time t. Then what is the distance covered? The distance covered must be the velocity times the time. That is velocity into time. So the distance traveled by this cylinder at t time is u into t. Now the dragging force. There are two forces acting at this point. One is acting from left to right, which is the force due to pressure difference. Another is acting at this point from right to left, which is due to the viscosity coefficient from right to left. Remember the equation number 12, which was minus F equals to eta A du dy. If we rearrange this equation, just put the negative sign from left hand side to right hand side, then this becomes F equals to minus eta A du by dy. Now, since there are two forces, therefore this F is written as F1, because the force due to pressure will be written as F2. Now put the value of the area of contact, which is circumference into the length from here to here. Here to here, this length into circumference, which is twice pi Ly. So let us put the value of capital letter A, which is twice pi Ly. Other parameters remaining the same. So this is the dragging force in the opposite direction due to viscosity. Now this F1 is opposed by the pressure, by the force due to pressure. Okay, so F1 is opposed by the force due to pressure of flow, and this pressure is P. So you can convert this pressure into force very simply, very easily, by multiplying with the cross-section area. Now the cross-section means the cross-section of the tiny cylinder into the external pressure. So how does the cross-section, you can get this cross-sectional area? This is pi y squared. This is the cross-sectional area. Okay, I am showing you once again. This is the cross-sectional area. Okay, so the external pressure into the cross-sectional area, that is the pi y square. Okay, now at equilibrium F1 must be equal to F2. That is, the expressions of F1 is equal to F2 like this, and hence after having rearranged them, we can get this expression du equals to minus p by twice eta L into y dy. Now we have to integrate them by giving limits. When the distance is from here to here, at this point the velocity of the layer is 0. So the lower limit here is r, and that of velocity is 0. Whereas if the radius is y, then the velocity is u. So this way we can put the limits. Du has lower limit 0 and upper limit u, whereas y dy has lower limit r and upper limit y. So integrating the left hand side, we get the value u, and in the right hand side, without putting the values of the limits, we can get this expression. Y dy has integration y squared by 2, and if we put the value, then it will get y squared by 2 minus r squared by 2. And this, if this half is taken as common, then this expression is minus p by twice eta L into half into y squared minus r squared. That is, u equals to this negative sign merged with this parenthesis values, so they will interchange their positions. It will become r squared minus y squared. So it becomes minus p by 4 eta L. 2 is multiplied with 2, and finally within the parenthesis r squared minus y squared. This is the extension of equation number 12. Hence this is equation number 12a. Now we have to consider yet another cylinder. This cylinder with radius y had been showing as shaded area, but this shade has been removed now. This is being shown as a transparent cylinder here, because we are considering here yet another cylinder at radius y plus dy. Well, dy is very small. So let us consider yet another imaginary cylinder with radius y plus dy, so that dy is very small. And the cross section area between these two cylinders, that is the area of this ring. What is the area of this ring? Very simple. The width of this cross section, the width of these two cylinders, between these two cylinders, and the circumference of this circle. So what is the circumference of this circle? It is twice pi y. Whereas what is the width of this area? The width of this ring is dy. So when dy is multiplied with the circumference of the small circle, that is twice pi y, then the area of the ring is obtained. So the cross section area between the two cylinders is twice pi y into dy. Now what is the amount of the liquid? which passes through this shaded area, through this ring. Very simple. It is actually the cross section area into the length which is obtained after allowing it to move for time t. Then if u is the velocity, then what should be the time, what should be the length of movement? Now it is t into u. So if u is the velocity of that layer, then the length of the cylinder produced in t time is u into t. Okay, how does the cylinder move? Look, this way the cylinder moves to produce the length u into t. So the volume of this liquid which is obtained after passing through this cylindrical sheet is dV. Therefore the value of dV must be equal to the area of this ring into the length of the cylinder produced. So it is twice pi y into dy. This is the area of the ring. Then the length of the ring is u into t. So this is the value of dV. So we have dV equal to twice pi y dy into u into t. Then we have to put the value of u from equation number 12a. Just we have derived this value. What is the value? Now u equals to p by 4 eta L into r squared by y squared. So let's put this value here in place of u. So here all the other parameters remaining the same, twice pi y dy, and here t also, just the value of u has been replaced with this value. Now we have to integrate this equation by giving limits. So if the radius is r, then the volume collected must be v. From here to here, this much amount of liquid is collected, which is actually v, and at this point no liquid is collected. So if the radius is 0, no liquid is collected. If radius is r, then v amount of liquid is collected. Therefore the lower limit of v is 0 to upper limit capital V, from 0 to v, and the lower limit here is 0 and the upper limit here is r. So now let us integrate. Okay, so left hand side the value of integration v, whereas the right hand side we have to just analyze this like this dy and this y. So r squared y dy, and here y cube dy. Okay, so this is y cube dy and this is r squared y dy. What is the value? Now for this one the result is y squared by 2, and for this one the value is y to the power 4 by 4. Okay, and after having put the value of the limits, we get this expression r to the power 4. That means r squared into r squared by 2, minus in place of y we are putting r, so it becomes r to the power 4 by 4. So it becomes r to the power 4 by 2 minus r to the power 4 by 4. And what is the difference? It is again r to the power 4 by 2. So it is r to the power 4 by, r to the power 4 by 4. So this part is remaining the same, p pi t over twice eta L, and this part is r to the power 4 by 4. So eta, we get the expression of eta from here. Eta equals to p pi r to the power 4 by 8 LV. This is equation number 13, and this is the famous Poiseuille equation. And if you put the value of p as h rho g from this experimental setup, then we get this equation, which is written as equation number 13a. Okay, so eta equals to h rho g pi r to the power 4t by 8 LV. So this is the extended form of that equation number 13, so it is 13a. So I hope it is clear to all of you. Thank you. Have a nice day.